Hello, welcome to this course entitled Deep Learning for Advanced Vision Systems. My name is Mohammed Bennamoun from the University of Western Australia. So just a reminder, what is computer vision? So it's an interdisciplinary field which focuses on how machines and computers can emulate the way in which human brains and eyes work together to recognize, to visually process the world around us, around these computers. So what does it require? What would you need to do computer vision? You would need a sensor, for example, a camera, a normal RGB camera. You would need a computer, a processor, and you would need algorithms. What is it used for? Autonomous cars, image search, for example, Google image search, face recognition at airports, on Facebook, with CCTV systems, in healthcare also to process volume images like CT, MRI, for image analysis and diagnostics, and of course, for military purposes, for automatic target recognition and so on. It is a hugely important area of research. In fact, this is one of the statistics. It's expected that hardware and software or computer vision market is set to, or was set to increase from 6.6 billion to sorry. It was set to 48.6 billion by 2022. As I said, it's a multidisciplinary area which requires some knowledge in mathematics, statistics, geometry, optimization. You would need to know things about cameras, for example, smart cameras. Sometimes algorithms are borrowed from neurobiology. So if you understand how the biological vision system works, you can emulate it, you can transfer this knowledge to computer vision. It will require machine learning, of course, computer intelligence, robotic wisdom, control robotics, signal processing, because you need to process these images, and physics, optics, and so on. So this is a taxonomy of artificial intelligence and where computer vision fits. So you can process one image, just like here, a satellite image, for example, or sorry, an airborne image. You can process two images for stereo vision to infer the depth. You can process a sequence of images for videos. As I said, you can also process volume images for CT and MRI for medical applications. Our contribution has been extensive in the area of 3D surface imaging. I can illustrate that later maybe, and then so the difference between image processing and computer vision is that in image processing, your input is an image or a set of images, and your output is an image or a set of images. For example, you have this image here, and it's noisy, and you want to process it, to use image processing to remove the noise. Computer vision, on the other hand, the input is an image or a set of images, and the output is a decision. So this is accomplished with pattern recognition, decision theory, and machine learning. And so pattern recognition, you can classify it into statistical, using Bayesian paradigm, structural, and artificial neural networks, and that's where our interest is, to lead to deep learning and so on. Other areas of artificial intelligence include expert systems and others. So this is just a brief or broad taxonomy. So what is the problem in computer vision? Is it the sensor? Is it the processor, the computer, or is it because of the algorithms that we use? So when it comes to sensors, the human eye is not as, although it's a great gift from God, but it is not as perfect as it is because we need binoculars to see far objects. We need slow motion to see fast moving objects. We need, and now we have even microscopes to see tiny objects. We have with medical imaging like CT and MRI, we're able to see the inside of an object without even performing an incision. So maybe that's not the problem. That's not the hurdle to develop good computer vision systems. Is it, when it comes also to computing, even a calculator can perform better than an average person. But when it comes to recognizing objects, recognizing faces and so on, maybe a child can perform better than the most sophisticated computer, at least a few years ago. So so the most probable way on how to advance computer vision is to combine these three things to get the best possible sensors, to get a good computing power, but also to get ideal algorithms and the computing paradigms, just like deep learning, to be able to advance. And it is believed by the community, computer vision community, and robotics community that if we're able to develop systems or with recognition capabilities of a 2-year-old baby, language capabilities of a 4-year-old child, the manual dexterity capability of a 6-year-old child, how you grasp objects, and the social interaction and understanding of capabilities of an 8-year-old child, robotics and computer vision will advance enormously. So a typical computer vision pipeline would be of this sort, so at least a standard one, the classical one, sorry. So the input is an image or a sequence of images. So you take this image, you pre-process it to remove the noise and other artifacts, and then you extract features, maybe geometrical features, maybe color features, and so on. That would take you to a certain feature space. You then select the most appropriate features, and then you have a classifier to infer, to give you for example, if you're doing object recognition, so it will tell you this is a car. So it gives you the prediction. So with artificial neural networks, with deep learning, what you'd like to do is to replace this pre-processing, this feature extraction, this feature selection. You want to perform an end-to-end deep learning. So you want to learn the features. You want maybe to even allow the system to learn to pre-process the image. And you would like to learn also to allow it to learn your features and so on. So you would like to replace all these 3 blocks with just one block and perform a recognition, in this case, in an end-to-end manner, using an end-to-end deep learning system. So before we go into deep learning and details and so on, we would like to have a feel of what is neural networks and build a strong basis to be able to have a good understanding of what deep learning is. So neural processing. So what do you want first your computer to do in the case of computer vision? So you would like it to recognize objects, a car, an airplane, a motorcycle. You would like to classify, maybe this is an animal So you divide or recognize you have a certain number of classes, animal or cat, dog, and so on. You would like to localize it as well. So have a window around that object, which tells you, I've detected a cat in this image, and I've detected an object in this image, and this object is a cat. Or you want to do object detection, so you put a window around each object, okay? And that's it. You don't do, or you can maybe classify the red squares into cats, the blue one into dog, and green one into a duck. You also, so you want to do detection, you want to do recognition, classification, localization, you want to do maybe segmentation. So in this case, this is called semantic segmentation, where you would like to associate each pixel to a certain class. For example, here, all these pixels are given or assigned to the label sky. You have all these pixels here, which are assigned to building. This is the road, okay? So all these pixels correspond to the road and so on. The same thing here, this corresponds to a car, another class, and so on. So this is, you want to do segmentation. You want to associate, in this case, semantic segmentation, you want to associate each pixel to a certain class. Now, there are two ways on, if you want to use a deep learning system, there are two ways of, or actually a number of ways on how to do it. The main or most important one, because we talk about supervised learning, we talk about unsupervised learning, semi-supervised learning, self-supervised learning, and so on. There are a number of learning approaches. So let's look at the case of supervised learning. So you have a training set with your end-to-end deep learning system, which has the objective of recognizing an object. And because you're doing it in a supervised way, so you have a supervisor. You have somebody at the output, an agent at the output, which is when you feed your input here, and then you say this is a red car, then so the system predicts that this is a red car. The supervisor would say, yes, this is correct, this is not correct. And so it has some ground truth. It knows it has a ground truth there, which tells it what object it is when you're doing your training. And then you take that error, the error that the classifier has made, and feed it back to your deep learning to adjust its parameters, to change them, to modify them, okay? Another neural processing is clustering. In this case, this is an unsupervised manner, so you don't have a supervisor. So as it says here on the slide, unsupervised classification of patterns or objects without providing information about the actual class. So you don't have your supervisor when you're doing, actually you're assuming that that your deep learning system is able to learn by itself in an unsupervised manner. So the network must discover for itself any existing patterns, regularities, separating properties, and so on. And while discovering these, the network undergoes change. So when it's doing it, when it's learning, it changes its parameter, and this is called self-organization. So it adjusts by itself the parameters of the network without a supervisor. So by itself, it changes them. And so this is an example of clustering. So you're feeding to your network a number of objects, and you want to, if you want to cluster them by color, so you will have all the greens together, the reds together, the blue together, and so on. If you want to cluster them by shape, then these shapes would cluster together, would form a cluster. If you're classing them by size, so it depends on the criteria of clustering. So this is a big object, these are small objects, and so on. And basically in the feature space, when you look, if, for example, if this is the shape, the height and the width, for example, then if you go to this, if your x1 represents the height, x2 represents the width, and if you go to this feature space, you will see that this object here, or the pixels of these objects, for example, cluster in here. And then the small objects cluster in here and so on. But sometimes when you do the clustering, when you try to do the clustering, and you go to your feature space, there is no apparent clusters. So you're not able to have a boundary, a decision boundary, which tells you this is cluster 1, this is cluster 2, this is cluster 3, and so on. Another neural processing approach is called auto-association. So in the case of auto-association, your input pattern, you have a network, okay, which has learned to recognize triangles, circles, and squares. And if you feed it, later on, if you feed it a distorted pattern, it will associate it. It will associate it to the closest object that it had learned. And in this case, it will be a square, and your output will be a square. In the case of heteroassociation, so you have some sort of some sort of association of objects which are of heterogeneous manner. So for example, this triangle is associated to a circle. So this is like association. For example, you associate an actor to a certain movie. And now when you want to, you're given at the input a square or distorted square, then it will go and associate it and will tell you this is the corresponding association here, which is the rhomboid. And as I said here, if you, for example, I tell you, oh, okay, remember that actor who did this and this and this, and then and in that movie, and then you go and give me your output and tell me this is that was in that movie. Okay. Thank you.